All right. Now, is anybody trying to write an equation down that this describes? Do you know how to do that? Did I bring a pen? I feel like I did. I did. Paper. There we go. All right. So we're looking at number 69. A number. Okay, let's call that number x. Is there a number? Where'd it go? That is exactly one more than its cube. What would this side be? A number is x cubed plus 1. That's what you're trying to figure out, right? Now, you don't have to solve this. And again, this is related to that intermediate value theorem that we're going to talk about first thing. That was the last thing I kind of left off. Okay. So this is related to that. So that intermediate value theorem is very powerful and it's very simple, which is nice. Okay. So somehow this problem is related to that last question you asked me about. They're all related. So let's talk about this intermediate value theorem. Okay. You guys doing okay out there? You guys remember we have a quiz as soon as I'm done talking about questions? Okay. All right. You're all like, yes, Jeff. Okay. So intermediate value theorem. All right. Let's zoom out a little bit, Jeff. Let's get the book out of the way, Jeff. Real quick, let me tell you where this is. There it is. Page 122 is where this is. So the thing that gives the intermediate value theorem so much power is the very first requirement for the theorem to work. If I have a function f that is continuous, this is stupid powerful, continuous, on some interval a to b. Oh, let me make that closed. Make that closed interval. So if I'm given a function that is continuous on an interval, it could be continuous everywhere. It just has to be continuous on some interval. Let n be any number between f of a and f of b. All right, so in words, I'm going to draw the picture in a minute. So can you imagine? So let's draw a picture as we do this. So I have a function. It's continuous between a and b. And there's a lot of ways I can draw this. But if it's continuous, that means it's defined everywhere, right? Continuity has in it the fact that it must be defined at all those points. Yes? So there is an f of a and there is an f of b. Do they have to be where I put them just now? Nope. But this is just one way to kind of capture what it's saying, correct? The fact that it's continuous, I can connect these points any way I want to. Now, of course, I can't do something where it comes back on itself because then it's not a function. But aren't there basically like an infinite number of ways to connect those points? But what's got to be true about any way I do it? Because it's continuous. Could this go down here? Yes. I love you guys. It could go down there as long as eventually it comes back up here, yes? It's got to. And can it skip over anything? Because it's continuous. Yeah, so it can't teleport. So what must it do then? What must it do? Couldn't I have drawn it just straight? Yes. Right? Or couldn't it go up here and do some weird shit? As long as it comes back down to that point continuously, it can't teleport. So is there any way you could draw that with the restrictions I gave you so that it does not have an output in between f of a and f of b? I really want that to make sense. No matter what way you draw that, is it possible that there's some value in here, let's call it C, is that the line would never go through? Hell no. If you try to escape the output of C, you can't. You go, I'm going to stay below it. Oh shit, I got to go up. Does that make sense? If it's continuous, I have to give all the values as outputs between f of a and f of b. Because it's continuous. I can't jump over outputs, because then it's not continuous. So, let n be any number. Well, they call it n. Why are they calling it n? Oh, that's right, because they got it backwards. Let n be a number. Let's call it n. Between f of a and f of b. There must be at least one. Let's go with this guy. There must be at least one input that has that output. There must be at least one C that is in A to B where f of C equals n. Now, of course, in theorem speak, it's easy for the idea to get lost. But the idea is remarkably simple. If I have a continuous function, it starts here and it goes there for the outputs. I've got to hit every output in between those. So what does that mean for a practical problem like, what was that, 51? Okay. So how does that apply to 51? Well, can somebody tell me, is that function I'm working with, does the central limit theorem, that's statistics, does the intermediate value theorem work for that function they've given me? What must be true about that function in order for the intermediate value theorem to work? It has to be continuous. Is it continuous?
Yes.
Yes.
Why? That's polynomial, that's continuous. That's trig, that's continuous. This is a combination of two continuous, so it's continuous. Everywhere on their domain, and of course, what are their domains? All real numbers. So this bad boy is continuous from negative infinity to infinity. It is ready. So whatever its lowest is and whatever its highest is, it's got to hit everything in between those because it can't teleport and skip over outputs. So, okay, so now hopefully everybody gets the idea. And now the next step is, what's the nuts and bolts associated with this idea? How do I answer this damn question? So, if I want an output to be 1,000, all we have to do, we don't have to solve the equation. It doesn't say I can use a graphing calculator, correct? And if you say x squared plus 10 sine x equals 1,000, do you understand there's no way in hell to solve that by hand?
Yeah.
No way in hell, right? So I want, let me just write it. I want x squared plus 10 sine x to equal 1,000. If I can find one input, I really want this to make sense. Let me write it like this. So this function, I think it's going to look a little bit like this. Dear Lord, I'm zoomed way in. It actually does not matter what it looks like. Can you guys see why it might look like that, roughly? It's still a sine piece, but the x squared is making it grow. And okay. You can graph it if you want to, but it's not going to answer the question. I want to figure out, is there a place where the output to this is 1,000? Woo! So what do we have to do? We just have to show that this function has an output below 1,000, and this function has an output above 1,000. Think about it. If you can show to me, you've already shown that that's continuous, right? We know it's continuous. If it has an output below 1,000 and it has an output above 1,000, doesn't it have to have an output at 1,000 because it's continuous? So that's all you got to do. Watch. What would you put in for x to be below 1,000? What's the easiest thing to show you can get below 1,000? 0.
Yeah.
What's the output for 0?
0.
0, right? Yes?
Yes.
Okay. Now, how do you get the other side of 1,000? I would just pick x to, maybe x 1,000 would work, like somebody said, but I want you to realize why that's a good step to do. You just have to pick another input that gets you above 1,000. So if it has an output at 0 and it has an output at 1,000,000, of course it has an output at 1,000 because it's continuous. It can't skip. Does that make any sense? Some of you guys are giving me thumbs up and stuff, and the rest of you are like this. I have no reaction for it. It's a remarkably simple theorem. It kind of, in one sense, is like, well, if it's continuous, then duh. And I don't say that to make you feel bad if you don't understand it. But if the function is continuous, of course it's got to hit everything between this and this. It's continuous. It can't skip. It can't jump. Right? Maybe? Yes? No? Screw you, Jim. Okay. One of those. It's a multiple choice option. Yes, no, screw you, Jeff. Okay. And that will also help you on, and I basically just gave you the first step for 69, was it? Didn't we write down an equation for 69? Yes? So then, and isn't it like a continuous thing? Okay. All right, maybe. And just to kind of go one more step, let me see, where did I write that equation down? I forget. Oh yeah, it was up there. All right. This was the one for 69, yes? Let me help you out a little bit. How many functions are sort of here? How many functions are kind of here? 2, right? There's 2 sides, there's 2 functions. Intermediate value theorem refers to 1 function, correct? Now do I have 1 function?
Yes.
And what do I want to show? I want to show that it has an output of 0. Isn't that exactly like the one we just did about 1,000? So in this case, I just have to show that it has an output that is negative and an output that is positive. That's right.
Positive.
You're good. I accept sleepy answers. Set. All right, that's all I'll say about that. That theorem is stupid powerful. It's going to be a building block for more complicated theorems. Intermediate value theorem is going to come up a few more times. Okay, I'm hoping it's simple. It gets a little weird how to apply it sometimes, but most things come out to be something like this. It's just, can you write it in this form? Okay. Anything else? 2.1 through 2.5 is today's quiz. So any other questions? 2.1 through 2.5?
I know we probably don't have time, like before the quiz.
Yeah?
But
You never know.
Can we do a little bit more on proofs?
Proofs. Oh!
Because,
I'll say this. There's no epsilon delta proof on here.
oh my god,
Yeah.
right.
I love you guys. You guys did that.
I was up till
That
1
was,
figuring it out.
Yeah,
I
the
cannot-
thing I
I
studied
I'll tell you
the most.
this. You need to do the homework, but it's going to be like a bonus question on the test.
That was the only thing
Yeah, I
Oh!
can't,
Shit.
yeah. Everything else
Why
is
did I
fine.
bury the lead?
Oh my god.
Why did I bury the lead?
Literally, it took me so long.
Okay.
You're like, everyone's like, yeah. Everyone's like, yeah.
Yes.
I cannot.
So look at me. Look at me. Look at me. So that whole section, I want you to do the homework. I want you to know exists. I need you to know what epsilon and delta mean. I need you to get a feel for the idea, but it's not going to be a main focus of what we're going to do. That kind of proof becomes a focus when you get up to like Math 284 or something. If anybody's going to go that far, then you focus a lot more on complete proofs and stuff. Or 285 later, yeah. But that epsilon delta idea is a part of so many other theorems throughout calculus that's why I want to go through that. So you just have that in your brain, right? Okay. So that makes me feel pretty good about this.